Okay, this is just a way to describe some of the processes that go on. It's called using eddy angular momentum fluxes to describe the tropical cyclone development. So we are still talking about the vortex, incipient vortex survival and evolution. So this is more about the processes and how they contribute to the evolution, and maybe also re-strengthening in some cases. So you have total azimuthal and radial velocities feeding the cyclone towards the eye wall, and you can write that essentially based on our earlier statements that we have essentially symmetric cyclone, and anything that is asymmetric within it, all the cyclone processes are creating symmetry around the eye wall, idealized in many cases, but the environment then can have an asymmetry. So to look at what are called eddy fluxes, they are deviations from the background environment. You can write U and V as U bar plus U prime, where U bar is the environmental background part and U prime is the eddy component of the azimuthal and radial velocities. You can then write the inward flow of angular momentum. Remember, the feeding the cyclone is coming from outer circle and circling in to the eye. So the R from the eye of the cyclone is changing, so you are changing the angular momentum, and you are decreasing R, so you are increasing the angular momentum flux. So you can write that as distance R times U times V, minus because it's going in. On the upper anticyclonic outflow, you would have R times UV in a positive. So if you substitute this eddy description into the U and V here, you end up with these terms: U bar V bar plus U prime V bar plus U bar V prime plus U prime V prime. I think many of you have done this kind of decomposition before. So you split that as a linear operation of averaging into minus R U V bar. So you have the minus sign inside here, so be careful. Minus R times U prime times V bar, so each of these terms, and obviously the U prime average terms drop out, V prime average terms drop out, so you are left with R minus R U bar V bar minus R U bar prime V bar. So that term R is not split into eddy and mean, and this term, and you can write this expression this way by ignoring the appropriate terms. Okay, what does that give us? You want to basically understand the flow in terms of the primary tangential circulation that's feeding the cyclone, and you have these secondary, what are called in, up and out transverse circulation that's happening because of these rain bands. So there is the eye wall, and it has its own secondary circulation, and the outer rain bands have their own secondary circulations with rising motions to feed convection and rainfall, and divergence above, and then sinking flow, right? So just think of these two circulations, and you have this subsidence in the eye wall and the associated pressure drop, warming and compression, and so on and so forth. And now we are going to look for the eddy flux contributions to understand how the process of eddy cyclone growth or evolution happens. We have already seen that the vortex is highly stable down in the lower levels, but as you go to the upper level, the stability of the vortex drops off, which is what we had seen before. So we are going from the outer edge of the cyclone towards the interior, and you can see that the outer edge, the stability is shown here as F0 squared, and as you come towards the eye, stability increases 10 times F0 squared, but it's high near the surface and drops off towards the upper levels. And the same thing happens here for eye wall and the inner rain bands. So our eddy angular momentum flux coming in is written here by dropping the appropriate terms in this expression. This term should go to 0 and this term should go to 0, so you should only be left with this and this. So you are left with minus RU V bar becomes minus R U bar V bar minus R U prime V prime bar. So it's the average of the eddy momentum fluxes, right? The main thing to understand here is that the eddy angular momentum flux is cyclonic coming in. So we are looking here at the cyclone center. So U prime, just think of the directions here. So if X is in this direction and Y is in this direction, so this is in the northern hemisphere. So you have U prime is greater than 0 and V prime is greater than 0. So actually we are going in the direction of the rotation of the cyclone. So that's why U prime here is 0. So U prime V prime is shown here. So cyclonic angular eddy flux momentum, eddy angular flux momentum is being brought into the center, which should make the lower part of the vortex stronger. But as the flow goes up and out, you have U prime becoming less than 0 and V prime becoming less than 0. So you still have their product to be greater than 0. Okay, both were positive here, both are negative here. So at the upper level or out here, you are taking out anticyclonic angular momentum. So you can do the signs in the lower level and the upper level. So U prime bar radial in, tangential and cyclonic components being shown here. So the transport of eddy angular momentum flux in a cyclone relative framework. Inset shows winds, wind vectors and potential vorticity contours shaded for PV units of greater than 1.5 on a constant potential temperature surface in the upper atmosphere. The storm's central pressure was 997 hectopascal. So U prime V prime greater than 0 leads to inward transport of angular momentum, and here you have outward transport of angular momentum. Okay, so you can see this is the cyclone we are looking at. So the main point here is that when we talked about things like Hurricane Diane, we started as a subtropical storm and managed to put vortex down to the surface, which strengthened. And in this case, especially model studies show that there was angular momentum flux convergence into the cyclone, which allowed it to strengthen and intensify, and the outward transport of anticyclonic angular momentum at the top will make the top of the vortex weaker, but that is almost decoupled from the inflow of eddy angular momentum flux in the lower part. So that outflow at the top is out of balance, but the inflow in the lower part is strengthening the vortex, so stability is increasing. So the outflow above then will generate the secondary flow that we are talking about here. So these outflows can still drive the stronger secondary inflows, which strengthen the lower part of the vortex. So even though the stability is different and the impacts of eddy fluxes are different in the lower part and the upper part, you can still intensify the cyclone. So this is a way of another way of describing how the processes of primary and secondary circulation within a symmetric cyclone and its interaction with the environment, which is asymmetric, can intensify the cyclone. And a good example of that was Hurricane Diana in 1984, which went through this intensification through the eddy fluxes in the upper part, driving stronger secondary circulation. So just keep that in mind. There are papers written on these types of processes, and it is part of the series of processes that we looked at for incipient vortex to evolve and survive, right? Survive and evolve. Okay.